We've been talking about projectiles, which are objects that are in free fall that happen to be moving forward at the same time. So to physicists, remember free fall means that your object is subject to only that vertical downward force due to gravity. There are no forces, there are no accelerations in the horizontal direction. When we are solving projectiles problems, your horizontal stuff and your vertical stuff are entirely independent of each other. What happens in the x direction doesn't affect what happens in the y direction, and what happens in the y direction doesn't affect what happens in the x direction. So whenever you are reading through a projectiles problem, as you are recording your givens and your unknowns, you want to make a little table and split your data into x and y. Now, here we have a gazelle. This time the gazelle is jumping off the cliff at an angle. So this initial velocity, it's not really solely in the x direction, and it's not really solely in the y direction. It's a diagonal. So we're going to have to work to split that into components, which is just a little trig thing. So there is a horizontal component there in red, Vx initial, okay, and then the upwards blue component, Vy initial. Okay, since this is a right triangle, I can assign each side hypotenuse, opposite, and adjacent. And then I can use my trig definitions to figure out how my horizontal components and my vertical components relate to the hypotenuse, which is usually given. Okay, so in the horizontal direction, usually you're going to be using cosine. Rearranging, you get that the initial x velocity is the hypotenuse v naught times cosine theta. Similar thing in the y direction. You end up getting that the initial vertical velocity is equal to v naught times sine theta. It is going to work out this way, the majority of the time. So here's some other variables. A similar scenario as one that we've discussed before. I love gazelles. I would never want to hurt a gazelle, so I'm placing this soft and squishy mattress at some horizontal displacement from the bottom of the cliff in order to save that gazelle's life. So making now our table for x's and y's. So here in the x direction, my initial velocity is v naught times cosine theta, moving to the right in my picture. Since the acceleration in the x direction is 0, I can, instead of calling this Vx initial, I can just call this Vx, because if the acceleration is 0, the velocity is going to be the same at the beginning, at the middle, and at the end, okay, in the horizontal direction. Obviously, we're looking for delta x. In the y direction, Vy naught is equal to V naught sine theta going upwards. My delta y, my displacement in the y direction, is the height h downward. And at this point, you might be saying, well, wait, why aren't you just putting a negative sign on that? Well, I could, right? And I will later on, but sometimes you want to be able to pick which direction is positive and which direction is negative. So until I start plugging stuff into equations, I usually like to do little arrows indicating the direction. Okay? So the only thing that goes in both columns is time. Okay, everything else is separate. Okay, they do not carry over. I see people trying to plug in the x velocity into a y equation, and that will not get you the right answer. So you just need to be very careful, okay, when you start looking at the side where you have the most information. Okay, here looks like I have the most information on the vertical side. That is generally going to be the case. And because time is the only thing that carries over on both sides, you're probably going to have to solve for time first. Probably. So the equation, delta y is equal to Vy naught times t plus 1/2 at squared. Okay, this now is where I define my directions. I'm going to say all of my vector quantities that have up arrows are going to be positive. All of my vector quantities that have down arrows are going to be negative. So we would get an algebraic equation that looks something like that. And so there you can see where I've plugged in my negative signs. Be very careful. I'm going to go ahead and assign some numbers to this. So I'll say that h is equal to 60, the initial velocity is 10, the angle is 30 degrees, and I will round gravity up and say that that is going to be 10 meters per second squared. So this equation, when you do have a vertical component to the velocity, it is quadratic. I managed to pick out numbers where it worked out really nicely, where you can, what is this? I don't know. You factor it out and you solve it that way. You might have to use your graphing calculator, right, and find the zeros, or use the quadratic formula for that. So we have two solutions here. The negative solution does not mean anything in this case, because we are not interested in going backwards in time for our little gazelle here. So it's going to take him 4 seconds to reach the ground, or the mattress, I should say. Now that we have time, then we can go ahead and move on to the horizontal side of our equation, okay, where we know that since the acceleration is 0, we can use this equation delta x is equal to vx times t. Okay, it's important to note that this only works on the horizontal side. It only works if the acceleration is 0. This is the constant velocity formula. Okay, when we plug in those numbers, we get a horizontal displacement of 34.64 meters to the right, okay, of the base of the cliff. Okay, that's probably the most common question that they would ask you. They may also ask you, let me fast forward this a little bit. This is just a duplicate of the information that we were given at the beginning. They might also ask you about the impact speed. Now, if you can imagine the gazelle flying through the air, it's going to hit the mattress at a diagonal, right? And if it's hitting diagonally, that's not a purely X thing, that's not a purely Y thing. It's got both X and Y components. We need to kind of evaluate this separately and then put it together. So since we are good in the X direction, right, that X, Vx is the velocity at the beginning, the middle, and the end, since the acceleration is 0, okay, we need to find out what the final vertical velocity is. With the information that is given, we can use this v final is equal to v initial plus at equation. Okay, again, plugging in my negative signs only on the downward acceleration due to gravity. We get a final y velocity of 35, negative 35, which means that that velocity is downward, which makes sense. Okay, we are not done. A lot of people get to this point, they're like, whew, did all that hard work, I'm going to take a break. Remember, to find the impact speed, that is diagonal. We have found just the downward component so far, but we know what the horizontal component is. Okay? And we combine these together using Pythagorean Theorem. Okay? When you have vectors that are perpendicular to each other, the way that you add the vectors has to be through a right triangle. You do Pythagorean Theorem to find the hypotenuse or the resultant vector. So when you do that, we get 36.06 meters per second. Okay? Finally, last but not least, the very, very last possible thing that they could ask you would be, what is the angle of impact? Okay, and let me tell you what not to do. Lots of people look back at the little picture with like the cliff, and they're like, oh, so the angle of impact, it's going to be, you know, this little angle down here in the corner next to the mattress, right? Wrong. No, don't do that. Okay, the angle of impact has to do with your impact velocity, not your impact displacement. Okay, the fact that your vertical component of the velocity is getting bigger and bigger and bigger, right, as you go down, okay, that triangle is not going to be similar to your displacement triangle. Okay, instead, you have to look at that velocity triangle that you just made. Okay, with this information, generally you're going to be using tangent because you have the opposite leg, which is usually your vertical side, and your horizontal leg, which is your x velocity. You work that all together and you end up getting 76 degrees below the horizontal. Whew.